So context of this is kind of traditionally, organic materials have been used in storage devices, in batteries and supercapacitors, but they tend to be used not as the redox active component. They might be used so typically as the electrolyte in solid state devices. You may have polymer electrolytes. They're often widely used also as binders as a way to sort of accommodate the changes in volume that come along with phase changes of materials as they become, of the electrode materials as they become charged and discharged. So then a question we started to think about a few years ago is whether we could use organic semiconductors as a redox active component. And if we wanted to do that, then there's a long list of properties that we would like to have. Amongst them, sort of obviously the appropriate redox potentials, high charging capacity, fast charging and discharging, and reversible behavior would be things you'd look for, as well as the ability to sort of make materials from sort of abundant non-toxic components, and ideally to recycle them. So if you think about what you expect from an organic semiconductor, you might expect it to do maybe rather well on the side of things like mechanical stability, abundancy, processability, and so on, and rather badly on the side of the specific capacity, because of course you have a low electron density, you can never charge an organic material very deeply. And then for all the other aspects, we don't actually, or we didn't actually know very much. So some approaches had been taken in the past literature to using polymers in storage devices. So doped polymer electrodes had been studied in the past. So things like PDOT, where you have a dopant present and you charge and discharge the material, removing and reinserting the dopant. There's also been work looking at the possibility of using polymers in redox flow batteries, which is interesting. It's a very different direction. And then closer to what we're doing, there have been a number of studies where polymers have been used as supercapacitors, and they're particularly interesting because of the compatibility of conjugated polymers with aqueous electrolytes. I give two examples here. The one bit below is a study from Linköping, a very nice study where you have a conjugated polymer with polar side chains and another polymer which has no side chains, and as a consequence it has to be deposited from a sort of as a kind of in a slightly more complicated manner, let me say, than processing from solution, but nevertheless a very nice approach. Now our approach was really to see, can we do everything with the conjugated polymer? I don't mean all functions of the battery, but all functions of the electrode. So to not require any dopants, not require any binder or any additional conductive element, but try to rely on the different sides of the polymer to fulfill the different purposes. So we would use the conjugated backbone for all the electronic properties, so to define the redox properties, the transport properties, and the capacity. We would then use the side chains to interact with the electrolyte and the solvent. So they would be responsible for controlling the take-up, transport of ions, and for the interaction with the solvent. And then the properties of the polymer as a whole, its molecular weight, its crystallinity, and so on, would control the properties of the electrode film, how easy it is to process, its microstructure, how resilient it is under sort of the interaction with the electrolyte charging, and so on. And the goal of this is then to have a solution processed electrode with mixed conductive properties, and that can be cast as a single phase. And then our idea was to embed such to use such a material as the positive and the negative electrode in a two-terminal device, and operate that ideally with the saltwater electrolyte, where at one side you would have a p-type polymer, which would become positively charged and take up ions, chloride ions in this case from the electrolyte, and the other side an n-type polymer, which would take up sodium ions, and then when discharged, it would release those and deliver a current. And that having those, and we would need to try to do those, if we're working in an aqueous electrolyte, we need to try to do those reactions within the electrochemical window of water, so we don't oxidize or reduce water. So this is how we that was the plan. And then we decided to work with a series of p-type and n-type polymers. The p-type is one, both polymers were made by the McCulloch group, and our primary collaborator there over this time was Alex Giovannitti, who was a PhD student and is now a postdoctoral fellow in Stanford. He gave a talk yesterday. The p-type that we used is a sort of quite widely used in this field, bithiophenene, an oxybithiophenene with alkyl side chains. It's relatively easy, it's electron rich, so it's relatively easy to oxidize, and it has nice reversible redox properties. And for the n-type, we used a version of the NDI-T2 copolymer that has both glycol and zwitterion side chains, so two different types of polar side chains. And the NDI-T2 is known to be quite relatively easy to reduce and also to show reversible redox properties. So these were kind of the two polymers that we did the majority of our first work with. And looking at the properties of the p-type, this is just showing the CV response, reasonably reproducible CV response, a bit of loss of performance after thousands of scans. And what is very nice about these materials is that because they're conjugated polymers, their state of charge is very easy to detect with an optical probe, because as you charge the material, you form polarons and eventually bipolarons, and they appear as changes in the optical spectra, and of course changes in the color of the device. So in the case of this p-type, as you cycle it, you see its color change from blue to transparent as this ground state absorption band is removed and replaced in the visible. Similarly, with the n-type polymer, we saw reasonably reproducible CV performance, some loss after thousands of scans. And again, we see very nice changes in color as the material is cycled through to the bipolaron and then to the polaron and then to the bipolaron state. And in this case, actually, both the polaron and the bipolaron have got signatures in the visible part of the spectrum. And so when you cycle the polymer, you actually see the color change twice. It goes from green to brown to gray and back again as it goes through the polaron and the bipolaron. In the case of the NDI-T2, the bipolaron signature is very characteristic. It's very easy to recognize. And that's something we're going to be using as a tool later on to study the stability of polymers. So, of course, for batteries, we're interested in the specific capacity and the specific capacity as a function of the cycling rate or C rate. And what's rather nice about the polymer films is that they maintain their specific capacity. It's not high, but they do maintain it up to sort of really quite high C rates relative to what is commonly found with battery materials. And this performance is maintained even for thicker films. The p-types are somewhat better than the n-types in terms of their sort of rate capabilities, but a little bit inferior in terms of their specific capacity at low rate capabilities. And something which is quite interesting here is that the loss in capacity in the best case when cycling at C rates of 10K is relatively small, and we think that can be improved because the rate is not only limited by the polymer, but also by the electrolyte and the contact. But something which is quite interesting here is that if we make a small change to the chemical structure, we actually find that the the specific capacity is strongly affected. So here we replaced the zwitterion side chain on the NDI with a polar side chain, and we lost capacity. That's something we're going to come back to. So then, putting things together, we have a system whose oxidation and reduction properties sort of fit more or less into the electrochemical stability of water. We made a device, almost like a dye cell. For some of you may have met dye cells in the past. We used that approach to make our simplest two-terminal device, and we could then measure the specific capacity and the rate capabilities for this device and show that the coulometric efficiency is pretty good, and the rate capabilities are also pretty good, with it maintaining its performance up to C rates of about 100K. We see the characteristic color changes in the battery, showing us that the bipolaron is formed in both materials. And we also measure the sort of stability of the device, and we find, perhaps not too surprisingly, that in the presence of oxygen, there is a loss in capacity, and that means that you need more charge to achieve a given cell potential if you work in the presence of oxygen. So of course, devices work better in the absence of oxygen. So what do we need to fix to try to make this performance better? So in the end, I mean, there's a number of targets. We want to have be able to control the ion accumulation and transport properties. We would like to be able to control and ideally increase the depth of charging and maintain a high voltage. We also want to try to improve the operational stability of our devices, and that involves both trying to eliminate, where we can, side reactions that we would prefer not to occur, but also dealing with the mechanical resilience. And most of these properties involve, in some way, although maybe a priori we might not know this, but they involve in some way the type of side chains attached to the polymer. So we decided to investigate the effect of side chains on the performance of electrode devices. And I just would remind you of this observation that when we were looking at the rate capabilities of our n-types, we found that replacing a zwitterion with a glycol side chain caused a loss in capacity of about a factor of 3. So it looked as though, although the polymer in some sense is exactly the same, the side chain is very important. And we decided to look at this in a bit more detail by designing a series of polymers which have the same backbone, but the side chains are varied. And we took this kind of this fully glycolated polymer and then replaced some of the side chains on the NDI with alkyl side chains instead of glycol side chains. And we then studied the performance as a function of that ratio of glycol to alkyl side chains. And so first of all, we show you the CV properties. There's a small shift in the oxidation potential to more negative potentials as you increase the amount of alkyl in the polymer, and it becomes less polar, I suppose. And that's more or less what you would expect if you think about what will happen to the dielectric constant of the environment. It's also what you would expect if you look at what happens to the interaction of the polymers with water. Because we also measured, and this was a collaboration with David Ginger's group, the take-up of water in the polymers, and even the passive swelling of the polymers is strongly dependent on the type of side chain. So the fully glycolated polymer swells a lot, and then the partially alkylated polymers swell, but not so much. We also look at the spectroelectrochemical properties, and as with the previous NDI-T2 polymer, we can see during cycling the very clear appearance of the bipolaron peak. That's very nice. This is for the 25% alkylated polymer. But for the fully glycolated polymer, we see the same features, but they're somewhat less visible. This was during the first cycle. So we decided to look at what happened during subsequent cycles. And you can see from the CV scans here that as you go through subsequent cycles, there is really quite a loss in performance of the fully glycolated polymer compared to the ones which have only 10 or 20, 25% of the glycol chains replaced with alkyl chains. We could probe this also by looking at the absorbance by the bipoleron. And during successive cycles, the totally glycolated polymer loses its bipoleron absorption really relatively quickly, whilst the partially alkylated polymers manage to maintain their absorbance over successive cycles. And the consequence of this is that if after a number of cycles you measure the specific capacity of the polymers, you find that it's really been very much affected by this loss in performance of the glycolated polymer, whereas with the partly alkylated polymers, the loss is much less and the specific capacity is more like what it is in the very first cycle. So this is quite interesting. We've also looked at the mass uptake under electrochemical charging by the polymers, and we find that in the case of the fully glycolated polymer, that there is a mass uptake which is somewhat irreversible from cycle to cycle, whereas in the case of the partly alkylated polymer, that effect is reduced. So it seems as though full glycolation is not advisable, doesn't lead to good performance for this polymer, but introducing a small fraction of alkyl side chains helps to impede these losses. Before going on, I want to make one point, which is that all of this work is done in degassed electrolyte. And when we work in the presence of oxygen, we still find that our polymers lose potential in the presence of oxygen. And this can be related to the reduction potential of the polymer. All of the reduced polymers in the polaron or bipoleron state are thermodynamically capable of reducing oxygen and leading to an oxygen reduction side reaction, which we think is going on. We're pretty sure it's going on because we find peroxide in the solution when we work in the presence of oxygen. So that's a problem that still has to be solved. Strongly, these are calculations here that show that simply showing that molecules that are known to be air stable should be air stable, but our polymers are not yet amongst such materials. So this is our kind of cartoon of what we think is going on, that when you have a polymer whose structure allows uncontrolled water uptake, that then leads to a kind of mechanical degradation of the polymer film during repeated cycling, and we eventually lose the polymer and it begins to break up and can no longer charge fully. That doesn't yet tell us anything about a microscopic mechanism. And to dig deeper into the mechanism, I'll just say a couple of words about work that we started. So we decided to avoid any issues to do with working in oxygen. We decided to look at the same problem in the case of a p-type polymer. And we looked at a series of p-type polymers with a different fraction of alkyl and glycol side chains. And the interesting thing we have observed is that when we have replaced a small fraction, 10% of the glycol side chains with alkyl side chains, alkoxy side chains, this doesn't have any negative impact either on the oxidation potential or on the specific capacity. They work more or less just as well, but in terms of their cyclability, they're much more robust to repeated cycling. And to try to investigate this, we wanted to understand what's going on with these side chains at a microscopic level. And that led to the study which Nick Siemens spoke about yesterday in some detail, where we've done molecular dynamic simulations on models on these PGT2 polymers with different fractions of side chains. And then we look in detail at the type of structures that are formed by the different side chains. This is the image of the structures formed by alkyl side chains when you have just 10% of alkyl in and 90% of glycol chains polymer present. And it appears that these chains are able to form some kind of connected, or if you like, percolating structure. Whereas if you ask the same question with 10% of glycol side chains in alkyl, you don't see the same degree of interconnection. And we believe this is due to the way in which the alkyl side chains like to interact in the presence of a strongly polar environment. So this is work in progress. We hope to gain some more insight into the mechanism. So to conclude, I would sort of first of all like to say that I think there's a lot of potential in using organic mixed electronic ionic conductors for electrochemical storage applications. We made a 2-terminal battery device and observed some interesting things. It can charge rapidly. It has a relatively low specific capacity, as you might expect for an organic semiconductor. It would work quite well in neutral salt water, but still has a loss of performance in the presence of molecular oxygen. We then did a detailed study on the effect of side chain structure on the performance of N-type and also P-type devices. And we found something quite interesting, which is that whilst full glycolation causes uncontrolled water uptake, a loss of capacity and electrochemical reversibility, a small degree of alkylation is able to maintain reversible performance. And that has led us to try to dig into this is supposed to say detailed understanding of side chains is necessary. It's led us to dig into understanding better the side chains. So that's it. I will finish by thanking my collaborators in this work. So I need to particularly thank the 2 people who started the whole process off, who are David Amoya and Alex Giovannitti, who were postdocs at Imperial. David is now in Stuttgart and Alex is now in Stanford. I'd like to thank Petruccia, who made a lot of the polymers for the N-type study. And I'd like to thank Nick and Hang and Sachitan, who are carrying on the work in our group at the moment, and our collaborators, Achilles, Lucas and David, Brian, for their contributions. Thank you very much.